And what we do is to see how much two things are entangled. What we do is we construct the reduced density matrix of a subsystem. We look at and the reduced density matrix of the subsystem will have some entropy. The amount of entropy is a measure of the entanglement between the two subsystems. So this this part may just, I'll skip this part. So we have, so I just quickly revised what is bipartite entanglement. Now the thing is, see, like I like this quote that I saw in a PhD thesis, that all separable states are alike and each multipartite entangled state is entangled in its own unique way, let's say. So there are many different measures of multipartite entanglement. So the one measure we are going to be looking at is something called K uniformity. So uh, like an n qubit pure state with the property that every k qubit reduced density matrix of these n qubit states is maximally mixed. These are called K uniform states. It's like the state has maximum bipartite entanglement across every K versus n minus K bipartition of an n qubit system. So this is one possible measure of multipartite entanglement, that you could look at maximizing or looking at the bipartite entanglement across all bipartitions or many bipartitions of a multi-qubit system. So like, for example, if you have a 5-qubit state, we can call this one uniform if all reduced density matrices of 1 qubit are exactly equal to identity. Like that's when you have maximum entropy. Or all reduced density matrices of 2 qubits is proportional to identity. So now the maximum this quantity can take, as in the k value can take, is n by 2. That's because both bipartitions have the same entropy. So states for which you have exact like states which are n by 2 uniform, right? This is a very strong constraint on a state, right? I mean, if you just write down an arbitrary state with a set of arbitrary coefficients and then try to put this constraint that all bipartitions should be like maximally mixed. That's a very strong constraint, and it's an interesting like mathematical question in itself whether such states do exist. And it turns out that such states, like the first work on this was done by an earlier paper. Oh yeah, this paper, 2008 paper, which shows that such states do not exist for n greater than 7, greater or equal to 7, sorry, for greater than 7. And this very recent PRL in 2017 showed that it's not, such states are not possible for 7. So this is the case of qubits. Such states can exist for higher, uh, like there are individual things like you have Q trits or and so on. If you have n level systems, d level systems, you can, such states are possible. But for the purpose of this talk, we will stick to just qubits. So now these are the Pauli matrices. I'm using this notation I for identity and X for the Pauli X, Y for the Pauli Y, and Z for the Pauli Z. So any general state can be expanded in this form, right? Any single qubit state can be expanded in this form. And this is called a block expansion. And there can be a generalized block expansion. Like you can write any multi-qubit state as a tensor product, as an expansion in terms of tensor products of Pauli matrices. So why okay, so the thing is, why is this important? So when you perform this expansion, okay, so in this expansion, like if you look back at equation 14, you'll see that the coefficients in front of each Pauli matrix is the trace of like rho z, or that is actually the expectation value of that operator, right? You're expanding a state in terms of tensor products of Pauli matrices, which are Hermitian operators. They're physically measurable objects. And we are expanding a state in terms of these expectation values of physical quantities. So we can show that for a k uniform state, the expectation value of all operators up to all operators acting on up to k qubits is 0. This equation 16. Now, what this means is for a k uniform state, like let's say operator acting on just 1 qubit, right? Like a Pauli operator acting on 1 qubit is something like it's a dipole moment. Like if that is 0, then dipole moments are 0. If operators acting on two sides are expectation value of that is zero, then quadrupole moments are zero, and so on. So there is a physical implication to like having this kind of entanglement, right? You're placing a very strong constraint on the overall structure of that multi-qubit state that all these expectation value of all these higher order moments are zero. So I think that from that long title I've looked at what is the multipartite entanglement that we're talking about. We're looking at this object called K uniformity, and we're looking at and what it means for something to be K uniform, and this idea of operators being with the uh, expectation value of certain strings of Pauli operators. They're all zero. So now let's look at the next part. We're going from there to error correction, right? So first I'll just do a quick recap of what is classical error correction. So in error correction, the idea is always like a trade-off between redundancy and error protection. As in, like, let's say I'm saying something and it's not clear, and if I repeat it a couple of times, it's likely that there's less chance for error. So basically, you're doing a trade-off between how much extra information you have to say versus what is the chances of error reaching the receiver. So now, like a very simple idea of this repetition is something like if I want to send, let's say, a string of zeros and ones through like a binary information through a channel, through a classical channel, I can encode each zero as three zeros and each one as three ones. So it's just repetition. Now, what can happen is you can have, let's say, a single bit flip. And if there is a single bit flip, you will get the string of three zeros can go to these four possibilities. The string of three ones can go to these four possibilities. But these two sets of errored or states do not have any intersection, right? They are distinct or mutually exclusive sets. So this is the basic idea. You try to encode some information in a larger space such that the set of possible errors will take you to two distinct, distinguishable sets of code words. So this is the criterion for an encoding being error protected in classical error correction, right? And once this is possible, once errors take something to different spaces, there will always exist some mechanism to decode your required information. Like it doesn't have to be unique. There can be different ways of decoding. So one possible thing in our case, this is the classical example again. We're looking at something like let's measure let's say the bit, uh, the first bit, and then add it to the value of the second bit. When I add, I see mod 2 addition. So comma, like let's make a vector which is z1 z1 plus z2 mod 2 plus comma z2 plus z3 mod 2, and this will give me some vector like this 1 0. And if it's 1 0, it means that I have to apply a flip on the first object. 1 1 means a flip to the second bit, or 0 1 means I have to apply a flip to the third bit. And this way I can recover the original information. So even in classical error correction, the basic idea is first you encode from there is some logical information that you encode in a larger physical space, right? And the second part is that this encoding should be such that the set of possible errors will take your code words to different sets of things which do not have
closely
any,
associated with
which
quantum
are mutually
communication,
exclusive or distinct or distinguishable,
this
right?
part of government
And
of
the third
India,
part is there
to
should
see
be
that
some
things are being
decoding
implemented. So
mechanism,
now I
right? In
request
classical
Anita
computing, the
to
decoding mechanism exists automatically. Once you have this distinct, because anyway, two binary strings are always distinguishable. You store a string of zeros and ones on the computer, it's always possible to read this without any problem. But in quantum mechanics, measurement is a much more non-trivial process, right? The measurement itself could completely corrupt whatever information you plan to store. So some further thought will be needed for that. So in quantum, like what are, so in classical, the errors are always like things are basically just bit flips, right? You're sending a string of zeros and ones, and some of those bits will flip from 0 to 1 or 1 to 0. So, but in quantum mechanics, you have a string of, let's say, qubits being sent through a quantum channel. All kinds of unitaries can act on this. So basically, the quantum computation itself involves a series of unitaries acting on an initial state. followed by measurements of some of the qubits at the end of the computation. So errors come from other interactions, right? I think the interactions that you don't want in the system. So between the system and the environment, which can be modeled as some unknown unitaries acting on a subset of the qubits. So if the
Thank you to
channels
Professor
carrying the
Panigrahi for
intelligence of the
organizing
quantum
this
computer are, let's
QIQT23.
say, separated well enough,
So
we can make the
I'm a
assumption that the
PhD
error can
student
be
here
described as a
at
tensor
School of
product of
Computing and
single
Information,
qubit
University
unitaries.
of Pittsburgh.
So
I'll be talking about.
So we are looking at errors of the form that are like tensor products of cube unitaries like x1 times z2 times y3 and so on. Errors of that form. We are not looking at errors which can entangle two bits like unitaries which act like together on two different bits or three different bits, right? We're not looking at any errors that can generate entanglement. So now, so we have looked at what is error correction now. Now let's see what is the connection between our measure of entanglement and error correction. So we already saw that for a K uniform state, the expectation value of all, let's say, tensor products of Pauli's up to n qubits is 0. Now this equation 21, you can rewrite it as, let's say, O(n), some operator acting on n qubits can be written as some different operator O1 acting on n by 2 qubits times some other operator O2 acting on n by 2 qubits. And now what we have is some operator O1 acting on n by 2 qubits on psi is orthogonal to some operator O2 acting on n by 2
Quantum
qubits.
distillation
This
with
operator acting on
quantum
psi.
switches in a quantum network.
So these two states are
So
orthogonal.
I'll
So basically
briefly
we have
talk about
two
what are
different
quantum
errors
networks,
breaking the state
and then I'll
to
talk
different
about the
states,
components
right?
of quantum
Like in
networks.
quantum mechanics,
So
different
quantum switch
or
is one of
distinct
the most
means
important
that they are
component,
orthogonal.
and then we
So we
figured a
are actually
policy.
satisfying the error correction criterion here just by this expectation value property of this entanglement. So now, so if psi is a k unit to state the point, so if psi is a k uniform state, it is a pure code capable of detecting errors acting on k by 2 qubits, like up to k by 2 qubits. So, so huh. Now the pure code part, I'll explain that a bit later. We'll get to what it means, why this is a pure code, and what is degenerate codes. So fine, we can go into degenerate codes. So this is something in classical computing. So in quantum computing, there is this idea of something called degenerate codes versus non-degenerate codes. Now this is not a distinction that's there in classical mechanics, like in classical computing. In classical computing, you only have degenerate codes, even though it might not be explicitly mentioned because there is no other. Sorry, in classical computing, there are only non-degenerate codes. So non-degenerate codes are the same as pure codes, is just another name for it. And so the degeneracy here is about how in 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 uh, in quantum computing, it is actually there are codes for which it is possible that you might not know what is the precise error that happened on a qubit, but you could still recover the initial information. Whereas, so those are called degenerate codes. There could be a range of different errors, and you may not be able to identify between them. But there could exist a correction procedure to actually recover your initial information. But this will not be the focus of our talk. But such codes are actually quite popular, and the Tori code, which you might have heard of, is one such code, like something called a Tori code, and this has some very interesting properties. But we're not looking at such codes. We are looking at something called non-degenerate codes, which are actually in some sense more classical. So, so like we saw in classical computing, you need this error correction criterion, and you need some way of measuring some sequence of measurements, and that will uniquely identify what error happened where, and then you apply the correction procedure. So in now we for K uniform states, we showed that that the error correction criterion is satisfied, that errors are going to different distinct states. Now the thing is, we also need a way to do measurements, right? So this is where we use something called stabilizer states. So psi is an n-qubit stabilizer state if, let's say, if psi is the plus one eigenvector of a set of operators, of n operators, which are linearly independent and they commute with each other. So then it's called a stabilizer state. Like, and SIs, the set of SIs are the stabilizers. So why is this important? One thing is because psi is an eigenvector of these operators. These operators are something you can measure without disturbing the state, right? I mean, if the state hasn't been, if there is no error on the state, you can measure these operators and you will get all plus ones and you will know that the state hasn't been disturbed, right? So you have some set of operators which you can measure. Now, and another thing to note is that let's take some error acting on n qubits now, and Si is also some Pauli string, so these two objects either commute or they anti-commute. These are the only two possibilities, right? They're strings of Pauli operators, so there's only two options. So let's say I can reverse their order and I will have a plus minus one based on whether they commute or anti-commute. And then Si psi is psi because psi is the plus one eigenvector of this. So I missed the plus minus one here. So we will get the same plus minus O psi. So what this means is that any errored state is also an eigenvector of the stabilizer operators, right? You will just get, if there is any kind of Pauli string acting on, let's say, the state, uh, you will get you will get some other state, and then if you do the stabilizer measurement, you will always get plus minus one. Now this is, so we do have a way of extracting a syndrome. By syndrome, I mean like you have a state, you pass it through a circuit, and then there are errors which act on this, which based on whatever model, and then you do a series of stabilizer measurements, and this will give you some. If there are no errors, you will get a string of plus ones, and if there are some errors, you will get a certain number of minus ones. And in certain cases, if the can, it is possible that this information can be used to correct the errors. So now about so there are also Hamiltonians which are composed of stabilizer operators. That is, there are Hamiltonians on spin systems.
Saurav, sorry for to interrupt. You have 10 more minutes. Okay.
Okay, okay.
Please keep in mind.
So maybe I should skip this Hamiltonian part. And so we have talked about why stabilizers are important. And so in the title we had multipartite, we were going for bipartite entanglement to multipartite entanglement, and we showed how this K uniformity is connected to error correction. And we have talked about how stabilizers are needed for being able to measure where the error has happened, right? So all this comes together finally in cluster states. So cluster states are a kind of, they are similar to, let's say, Ising model. Like if I look at this, you've seen equation 24. This is like a 1D Ising model. So in the cluster, the 1D cluster Ising, you will have three body interactions. You will have interactions um, like you see in equation 29 here. Each qubit on site I is interacting with a qubit before it and a qubit after it. So these are clusterizing things. And you can have d-dimensional, like a 2D version of this, where each qubit is interacting with all of its four neighbors. So there are five body interactions, and you can have higher dimensional versions of this. So this is the clusterizing thing. Now, people have already looked at this quite a bit, and in the past, and the 1D model, they have shown that this can show some interesting phase transitions between something called a symmetry protected topological phase and antiferromagnetic phase. And the 2D model has been shown to be useful in something called measurement-based quantum computing, like where instead of passing qubits through circuits, through quantum circuits where you apply all these logical gates and so on, you instead prepare a state and then you do a series of measurements from in some direction from left to right, let's say, and this is etching out whatever information you want onto that state. Like the final at the end on the right side, you will get the result of the measurement. So sorry, you will get the result of the computation. So instead of applying unitaries, you apply a series of measurements along one direction. So, so clusters 2D cluster state has been shown to be useful for this. Now, what in our work we have specifically looked at is that wait, here's the statement. Okay. So the specific thing that we have looked at is that we have shown that a dimensional clusterizing like is 2D uniform. That is, it can correct errors up to d qubits. So in like the 1D case, for example, it can correct just one error, and the 2D case can correct two errors, and so on. And this doesn't require an infinite lattice. It can be done on a finite lattice of 5 qubits along each dimension. Actually, the 5 qubits is more of a conjecture on our part. We have actually shown it for up to 7 qubits. That is the lower bound we have reached. So 7 qubits along each dimension. We and you can construct a lattice like that, and you can correct that many errors. So I think the outline of the proof is just some counting arguments. So what we have done is we have so for the 1D case, we have actually tried to do a simulation on a quantum computer to show that this works. So the thing is, this kind of compared to things like degenerate codes like Tori code, it's not very efficient in terms of how much redundancy you have versus how many errors you can correct. But on the other hand, there is the advantage that you can know precisely which error happened on which qubit. So the application that we have proposed was that we could use this for benchmarking existing quantum computers. Benchmarking as in like you check the error rates on certain qubits. I mean, that can be done by other methods, but this is one other method to do that. So you have a quantum computer, you prepare the first part of the circuit is preparing the cluster state, and then you wait for some time, and some error could happen on this qubit, and we could do a series of measurements on that qubit and its neighboring qubits, which would uniquely tell us whether X, Y, or Z or nothing happened to this qubit, you know. And like this, we were able to benchmark. So the left side, we have a noisy cascade simulator, and here is on the real IBM computer. And then the last part is that, so the thing that we were doing, we have this error benchmarking thing, and we had a unique state, right? So if you talk about, let's say, some kind of quantum information, it has to be something like this, right? It has to be some alpha times some state plus some beta times some orthogonal state, right? Like an arbitrary qubit of information has to be something like that. One state is not a qubit, right? You need to be able to store some arbitrary information into this thing. So the thing is, the problem was that the clusterizing, that the ground state of that Hamiltonian is non-degenerate, right? So how do you introduce degeneracy? So a trick for doing that we have done is that we have this measurement-based protocol. We take some ancilla qubit in some arbitrary state that you want to encode using the cluster state. We apply control Zs between that ancilla qubit and some set of qubits of the cluster state and some set of qubits A. And then you measure the ancilla qubit with the X basis. Doing this will transform the cluster state into this alpha times cluster state plus beta times Z acting on those set of qubits times cluster state. And if the number of qubits you had initially applied control Z2 is greater than this number, you will have like a d-dimensional clusterizing will preserve its 2D uniformity. That is the error correction ability is present. So we are able to encode arbitrary qubits into the ground state of this cluster state, even though the ground state of the clusterizing does not have any degeneracy. So as a recap, the basic idea is that we have shown that the d-dimensional cluster state is 2D uniform, and this is the ground state of a stabilizer Hamiltonian with periodic boundary conditions of finite size. The uniformity and / the multipartite entanglement of the state allows non-degenerate error correction. Non-degenerate error correction specifically means that you are able to identify what errors have happened on which qubit, right? And in degenerate, you cannot really identify what error has happened where, but you can recover the earlier information. So even though code distance scaling with redundancy is poor, non-degenerate error correction is useful in benchmarking applications. And cluster state was used to benchmark single qubit error rates in an IBM Manila quantum computer. And we have a measurement-based protocol to encode an arbitrary qubit with non-degenerate error correction ability. So yeah, thank you.
So I
Okay.
have a question.
Yeah, please.
Okay.
Sowrabh, so can you like tell me if I see this code in terms of like a NKT code, can we like know what is K and like what is D here?
As a NKT code, so wait, okay. So here the error K is the okay. So the original cluster state has just one. The K is just one, and
Okay.
the code distance, if it is D, the N is actually L to the power D, where L is 5. I mean, yeah, I guess is 5, 5 to the power D. So it's quite inefficient in terms of it's 5 to the power D, comma 1, comma D.
Okay. And like, is it possible to like do for like 2 qubit errors and like correlated errors? Like,
Yes, yes. So
so,
that's the D part, right? You can
yeah.
increase that. I mean, but then you
Okay.
would need a lot more qubits. Like for to be able to correct 2 qubit errors, you will need 25 qubits here.
Oh, okay. I see.
Like the
Thank
total
you.
logical, the total physical space will be 25 qubits.
Yeah. So like, is it better than the source code or like, so,
Uh, no, not exactly. It's not better than the short
okay.
code.
Okay.
It's
Thank
more
you.
like it was more like we had this. People are already looking at these cluster states from a physics point of view, the clusterizing and its properties, and it has this one extra thing that it's also the ground state is an error correcting code. So and yeah, we were just and it
Yes.
turns out there is some use, but yeah, it's not very practical for error correction.
Okay.
So yeah, I have a question. So you use this K uniform criteria of entanglement
Mhm,
of entangled states. So
mhm.
so could you just can you just tell me what is the motivation? Because for using this particular characterization, because there are also other forms of characterizing these entangled states like James multipartite. But is there any specific motivation behind this using this form of this particular K uniform and entangled state characterization?
Yeah, I can't really give a good answer for that. I can just say that it was more aesthetic than anything else. I mean, it seemed like a good measure, like in the sense of from a
Okay,
combinatorial perspective, right? I mean, you have a well-defined definition for what is bipartite entanglement. You can
okay,
extend that to multipartite by just talking about like multipartite means many bipartitions are possible. So let's try to maximize the entanglement across multiple bipartitions. So
okay,
initially, our search was trying to construct general stabilizer states which have this property. We didn't know that this had something to do with error correction. So we were just trying to construct, let's say, Ising-like models in which, for which the ground state will have very high measure of entanglement according to this criterion. Then we saw some work that this is connected to error correction, and so it became more about that.
okay, nice. Okay. Thank you.
Mhm.
Okay, so is there any other question? Maybe one question, quick question. If not, so let us thank Saurabh for this beautiful talk. So the next talk will be by Dr. Bhavanandi Pal. So he is working at MCKV Institute of Engineering. So he will be talking about